Whenever fluids interact with solids, there's generally going to be some pressure acting from the fluid onto the solid. There may also be some shear stress from the fluid acting on the solid. Those pressures and shear stresses can be related to forces. You can integrate the force over that entire area. That's trying to give me some pressure force. You can integrate the shear stress over that entire area. That's trying to give some shear stress force. In some occasions, these forces may balance, so the pressure on the top equals the pressure on the bottom. Shear stress is equal as well, in which case you get zero net force. But in other situations, those forces do not balance, and when they do not balance, you end up with two forces, generally broken down into horizontal and vertical components. So my horizontal component is what we call drag force. Vertical component is what we call lift force. So today's lesson is going to be dedicated to these horizontal forces, the drag forces. A couple lessons from now we'll see the vertical version, the lift force. So as we just saw, both lift and drag are calculated by integrating the pressure and shear stress over the area of the object. This leads naturally to two components. So specifically for drag, we have the pressure or form drag, which is from the pressure on the front of the object. So that depends mainly on the shape of the object. And then the second component is the skin friction drag that comes from the shear stress inside the boundary layer, like we talked about in the last couple lessons. Force over a flat plate, that drag force was just the skin friction drag because it was a really thin flat plate, so there's nowhere for any sort of pressure variation. So we were assuming that the pressure contribution, the form drag, was zero in those cases. So the way drag is usually calculated is through the non-dimensional number called the drag coefficient, very similar to the force coefficient we've seen before. So my drag coefficient is the force of drag divided by 1/2 rho v squared area, makes it dimensionless. But the way drag is actually calculated is usually you find this number not through this equation, but you find this number through some other means, kind of like we did for the flat plate, those equations we used. Similarly here, there might be some equations, maybe some tables, maybe some figures. So we're going to find a value of CD based on the situation, and then generally calculate the drag force using the same equation, just rearranged for drag force. So my drag force 1/2 CD rho v squared area, and then this area is generally the projected area facing the flow. So in other words, the way I like to think of this is if I have some object like this pen, a cylinder, I pretend I'm kind of the wind, and so I'm the wind coming in, hitting this object, and I kind of pretend that, what do I see? So if I'm the wind, what do I see? I see a top area that has a length which is equal to the diameter. I have a height which is equal to whatever length this guy is. So basically what I'm seeing here is a rectangle of area L times D. So that's the area I want to use in my force equation. So we saw for the flat plates we actually have equations that we could calculate the drag coefficient, or what we called the force coefficient back then. And those equations sometimes came from doing a bit of analytics, so a bit of math, sometimes came from a bit of experimentation. In general, if you have a very simple shape, like that flat plate or like a sphere, and very low Reynolds numbers, you can generally find equations. So again, for the sphere we might have some equations. For the laminar flat plate we had an equation that was derived from math to find the value of CD. But in most cases, complex geometries, higher Reynolds numbers, most cases the CD values are found experimentally. So you put the object in a wind tunnel, you measure it, and then that gives you the value of your drag coefficient. And so there's a bunch of graphs, tables that we're going to see in a few seconds here, telling you how to find CD based on those scenarios, based on those geometries. Recently though, with computers being more powerful, some people have started using computers, CFD, computational fluid dynamics, to calculate drag coefficients in various scenarios as well. So that's becoming more prevalent these days. So this is our first graph involving simple shapes, spheres and cylinders. Cylinders, I'm assuming that it is very long, so the length is much bigger than the diameter. Generally, want that to be as big as possible, so you get two-dimensional flow. That's what this is for. Generally, if the length is more than about 20 to 30 times the diameter, this is a pretty good approximation. So in that case, use this figure here. figure 11.2. You see the x-axis has Reynolds numbers, y-axis has your CD values, and of course the two lines, one for the cylinder, one for the sphere. Some students have had some problems reading this graph based on the fact that both scales are logarithmic. So you have numbers like 10 to the 0, 10 to the 1, 10 to the 2. So basically 1, 10, 100, 1,000. And then between each of those are 10 divisions. So between 10 to the 0 and 10 to the 1, I go from 1, then 2, 3, 4, 5, 6, 7, 8, 9, up to 10 to the 1, which is 10, and then 20, 30, 40, 60, up to 100, and so on. Similar figure 11.3, has a few other shapes. So in addition to my cylinder, I have other two-dimensional cross sections. So again, these guys are all assumed to be very long in the direction in and out of the page. So I have flat plates, both oriented horizontally and vertically. My cylinder again, so that green line should be the same as the red line in the previous figure. Stretched out circle into an ellipse, more streamlined airfoil shape, and then the red line for the flat plate horizontally, that's again the same figure we would have seen from the flat plate lessons. So if you did the laminar part, that's a straight line version up to 500,000, 5 times 10 to the 5th, and then the turbulent part takes over the curved part of the line that's bigger than 10 to the 5th. Other two-dimensional shapes are given in figure 11.4. So I have things like triangles, squares, semicircles, things of that nature. Again, two-dimensional objects here, so very long in and out of the page. Three-dimensional objects are next in figure 11.5. So I have actual cubes or discs, cylinders, cones, hemispheres. So now I actually have three-dimensional shapes, so the length is not much longer in the third dimension. And finally, figure 11.6. Again, three-dimensional objects, but these are more kind of everyday objects, not just geometrical shapes. Things like flags, parachutes, people, cars, trains, buildings, all sorts of fun stuff. So the procedure to find the drag is very similar to what we saw before for the flat plate. First thing you want to do is find the Reynolds number or any other necessary parameter we saw in the tables and the graphs. Some of them depended on Reynolds number, some of them depended on aspect ratio, things of that nature. So you may have to do this, you may not have to do this in this scenario, but find anything you need to find the CD value from those charts, graphs, tables, equations, whatever shape you're given, whatever the appropriate table or graph is for that shape. Then once you have the CD value, again, exact same as the flat plate, find your force using same equation, 1/2 CD rho v squared area. So example of this process, I have a vertical cylinder, modeled TV antenna by a vertical cylinder, and wind blowing across this TV antenna at 20 meters per second under normal standard atmospheric conditions, and want to know what the drag force is on my vertical cylinder, as well as the bending moment at the base. So solution here, following that procedure, I want to find the drag force. To find the drag force, I need to deal with a cylinder. So I want to find, how do I find the drag force for a cylinder? What table, what figure do I use? So in terms of the length to depth ratio, 30 meters going up and down, 30 centimeters in the direction of my flow, which means that in terms of the length perpendicular to the flow, L over D ratio is 100. That's more than 30. So I can use the two-dimensional approximation. So essentially, assuming that none of this flow goes around the top of this, it's all going around kind of out of the board. So that's where the two-dimensional approximation comes in, which means I can use figure 11.2 that we saw for spheres and cylinders. So that's what I'm going to use. To use that, of course, I need the Reynolds number. So first thing I want to do is find my Reynolds number, velocity length over kinematic viscosity. So I'm going to need the kinematic viscosity of air. Find that in table B3 to be 1.50 times 10 to the negative 5 meters squared per second. So calculating that Reynolds number, velocity, diameter over kinematic viscosity, I have 20 meters per second velocity, 0.3 meters, 30 centimeters for the diameter, and 1.5 times 10 to the negative 5 meters squared per second kinematic viscosity I found previously gives me a Reynolds number of 400,000. And one thing about this, on the previous board I had Reynolds number was velocity times some length over kinematic viscosity, and so why am I using diameter here instead of length? And there's two reasons generally. So generally the Reynolds number, the length I want is in the direction of the flow. So we saw for the flat plates, it was the length of the flat plate where the fluid was flowing over it. Same deal for these scenarios. You want the direction in which the fluid is flowing. So my velocity coming in this direction goes across that length. So that's the length that I want, the diameter in this case. Also, because I'm calculating the, or finding the drag coefficient based on figure 11.2, you'll see in the figure that I'm about to show you for this example that the bottom axis, the x-axis, specifically says RED, so it wants you to make sure you base that on the diameter for that table or for that figure. That's how that figure was calculated, using diameters. So two reasons to use diameter in this case. So with that Reynolds number, now I want to go to that figure to find the CD value. So as you just saw, from figure 11.2, that CD value is roughly 0.35, so that's what we're going to use. So now that we have the CD value, the last thing to do is find my force using the good old equation, 1/2 CD rho v squared area. So 1/2 my CD value I just found, 0.35. Density of air, standard conditions, 1.2 kilograms per cubic meter. Velocity, 20 meters per second, square that. And then my area, again, my projected area, length times diameter. So 30 meters by 0.3 meters. Multiply all that together gives me a total drag force of 756 newtons. So what that actually means is kind of like in statics, if you have a distributed load, you can take that distributed load and make it a point load in the center. That's kind of what that number is. So generally what I have is wind hitting this thing, and it's hitting it at the top, hitting it in the middle, hitting it at the bottom. So I have this distributed kind of wind drag force that I'm calling a point load in the middle. So that's what that number tells me. And then if I want to find the bending moment at its base, the second part of this question, so base down here, moment is a force times a distance. So I take this force acting in the middle times that distance. So middle of this cylinder is half the height, 30 divided by 2. So I take that force, 756, multiply by 15 meters, and I get 11,300 newton meters.